Let's get started. Thank you all for coming today. Happy that you all are at one of the first in-person talks of the semester, hopefully first of many. Bridget Smart has been a visiting student in the Complexity and Society Lab for the past 10 days or so, and she's going to be here for a couple more days this week. But it's been a great visit, and she's working on several really interesting threads related to information theory, time series, sequences and networks, network science broadly. So I'm really happy to have her here to talk today. So thank you. Take it away.
Thank you so much. Thank you both for having me for the visit and for the talk. It's been awesome to meet a lot of people who are here, and I'm here until Friday. So if anything in this talk sparks your interest, I'm on the Slack, or my email is on most of the slides, so happy to chat and catch up. To tell you a little bit about me, I'm currently in the third year, well, going into the third year of my PhD at Oxford University, where I'm working with Professor Renaud Lambiot in the maths department. And I'm also working with Professor Dylan Farmer at the Institute for New Economic Thinking. So I sort of sit between maths and quite applied social theory economics. And I'm thinking a lot in my work about how we can better model and understand complex systems. So I work on a range of different projects, but today I'm going to be telling you primarily about this project, the Separable Markov process, which is a model for generating sequences over networks. And the key motivation behind this project, and I'll obviously get into it a little bit more over the rest of this talk, is how can we simplify models while maintaining strong mechanistic interpretability and a good parameter space so we can apply them when we have limited data settings. So to get into it, let's start with a tiny bit of background. I'm thinking a lot in this project about dynamics over networks, and we think about models with dynamics over networks. I'm sure most of you have touched them in this room. And we're thinking about things like sequence generation. So what are people saying? How are they behaving? Where are they going to? What are they buying when they're doing online shopping? And all sorts of different applications. And fundamentally, these models look something like this. We're asking questions about where are we going to next if we know where we've already been. So the basic setup when we think about it over a network is often we represent the network as a transition matrix. So the weights on these edges represents either a transition probability or a rate at which we transition. There is a bit of an asterisk here, which is in this project, I think a lot about time agnostic sequences. So I'm just concerned with what sequence of nodes we're visiting, but you can add temporal information into these models. So you either look at continuous transition times. So walkers will sit on a node for some continuous amount of time, or they'll sit on an edge for a continuous amount of time. Or we can have discrete models where they either stay at a node or transition to a new node. But like I said, I'm not touching the temporal information in this project at the moment. So I'm really thinking about representations of these matrices, and I'm going to be calling it an underlying transition matrix, where the edges represent a transition probability from one node to the next. And a really, really common model in this space is a Markov model. For those of you who are not familiar, a Markov process basically takes this transition probability, so where will we be at time t, given we know where we were at every state in the history of the process, so t1, t2, all the way up to t minus 1, and we simplify it. We just say all we care about is the most recent state we visited. This model actually works really well in a lot of applications. The problem is as soon as we have a system where we have memory, so usually human behavior or economic models, the way that we transition doesn't just depend on where we just were. So you didn't come to level 11 because you were just on level 10 or whatever level your office is on. You came to level 11 to see my talk because you're here for your project, and this memory in the system is much, much longer than the most recent time step that we're looking at. And so a really common way to solve this problem is to just use a kth order Markov process. So what we do is we just extend the amount of memory which we have in the state space of this model, which works really well unless you want to fit your model to any kind of finite amount of data for a long memory, because we have an exponentially growing parameter space. So for a network with n states, and we want a memory of length k, our parametric requirement grows like n to the k. There are lots of people thinking about this model, and I'm just going to take the opportunity to plug some work from elsewhere within my group. So another PhD student, Rohit, who works with Renaud, is looking at a model which interpolates between first and second order Markov processes. So he uses this kind of model with a first and a second order memory, and allows states to either be first or second order states. So if this is something you're interested in, I highly recommend taking a look at this paper. But in my project, I'm thinking about it slightly differently. So I'm saying that if we start with this Markov process with a memory of length k, how can we think about and simplify what this transition probability looks like so we can retain a system with that memory of length k, but we kind of solve this exponentially growing parametric space. So to give you a tiny bit of intuition, when we're thinking about this Markov process with, in this example, we have a memory length of 3, the way we can think about these transitions is what's the probability that we transition to a state, for example, D, given we just visited A, B, and C. And you can really think about this as the whole joint history. We know the order which we visited them and we know when we visited them, but we're just concerned in that one single transition probability. And when we apply this kind of reframing across the entire transition matrix, we get a transition matrix which looks a little bit more like this. So each of the nodes in this transition matrix represent a history in that process of the memory length of the system which we're interested in. And so that is sort of where that exponentially growing parameter space comes from. Onto the separable Markov model, the intuition looks a little bit more like this. So what we do is we take a weighted distribution over each of the historical states which we care about in our system, and we sum using some kind of weights, which I'll talk about again in the next part of my talk, over each of these individual contributions for the process. So in the example I'm going through on the slides, if we're thinking about the probability that we transition to state D, we're thinking about that as the weighted sum of the transition probability from A to D, from B to D, and from C to D. And so what we can think about is, rather than thinking about that joint history, we're linearizing this dependence on the history of the process. And so slightly more formally, what we're actually doing is we're taking a subset of the full higher order Markov process, and we're rewriting this full joint history to look something more like that. So the different parameters in this model are our memory function, which we're using to represent psi. And what that is it's that weighting distribution across the historical states in the process. And so under this model, you can really think about it as separating the temporal information out. So this memory function is capturing how we care about the time aspect of the history of the process from the structural information which we're using to generate these sequences. And so that structural information is captured almost entirely by this transition matrix, which I've called A to the W. This is not A to the power of W, and I'm going to go through that in the next slide. This model is really nice. It's very expressive. We can have similar predictive capacity to a full Markov model. The issue being is that we're linearizing that dependence on the historical state. So we are losing a little bit of information when we move from the full kth order Markov model to this model, but we have a really expressive and well-defined correlation structure. So the way that I started exploring this model, actually, to give you a little bit of insight into the motivation, I was thinking a lot about how we could measure online social networks. And so when we're thinking about measuring aspects of information flows online, we're really interested in the distributions of what people are saying, so the words which are coming out of different accounts. And that's all well and good to test these models to simulate data from an IID distribution or a really simple Markov process. But when we want data which has really strange ordered correlation structures or long-range dependencies, using a model like this allows us to generate these sequences that have those correlation structures that allow us to test the, in my case, information theoretic estimators we were using to see how biased they became as we had more and more correlations in the system over a longer and longer time scale. And so this model is a really nice expressive model. And because we have all of the temporal information captured within that memory function, we can really carefully control what that autocorrelation structure looks like in the sequences that we're generating. If that's something of interest, I'm happy to chat about it a bit later. This is not a new idea. So when Markov processes were first introduced, different ways of parameterizing them were explored. This work in particular is quite a nice exploration of one version of this model. But in this work, which I'm doing, we're thinking about how we can sort of unify this framework and present it in a more general way. And so when we start with our separable Markov model, we can actually have 3 different choices for that underlying transition matrix A. So the first one is that we fix A across all of the temporal lags. So in this case, you can get some slightly counterintuitive results, but one really nice application to think of is if you're browsing online and you're clicking on links on different pages and opening them up into your infinite pool of Chrome tabs that you're never going to look through, how do you then choose which tab you're going to move to next? A lot of people will, sometimes I, especially when tired, will just randomly choose one of those pages or one of those tabs, or I'll see a little bit of information and click on it. And so under the first choice of A, what we can think about is this underlying transition matrix represents those physical links between the pages, and that memory function dictates where sort of along that Chrome window we're selecting our next tab from. So as that memory function becomes flatter and more uniform, we're just doing some random mixing through this underlying transition matrix. The second approach we can have is we can incorporate some temporal information into that transition matrix itself. So rather than just representing the physical links in the system, if we let A to the W be equal to the Wth power of A, what we're saying is when we're thinking about a step from lag 3, so W is 3, we're saying what's the likelihood that we transition from where we were 3 steps ago to where we're looking at next, given we want to do a hop of length 3. And so this can be sort of as resampling a Markov process. The final representation here is that we just let A to the W be completely free. And if you consider the difference between case 2 and case 3, you end up in this really interesting space of processes where you have the dynamics which are sampling that underlying structure of the system or that transition matrix changing in sort of the long, medium, and short term. So you can think of systems where the way you transition, if you're transitioning from a state that you visited a really long time ago, will be fundamentally different to how you're going to transition if you visited that state more recently. And so that is captured in space in case 3. And some future work which isn't in this presentation is fitting basically case 3 and case 2 to data and looking at how different those transition matrices are as W increases. So how can we identify systems where we have fundamentally different transition structures when we're thinking about further and further back in time? This model is really interesting, and we also get some really neat properties from it. So because we have this slightly more simple condition, you can get some really elegant results. Here's some old work I did which showed that the entropy of this model is the same as the first order Markov process, which is parameterized by the transition matrix when you have a fixed A to the W. And so intuitively, what we're saying is that the information captured by this model is the same as that first order Markov process with transition matrix A to the W when A to the W is fixed. And you can think of that as the extra randomness that you introduce with this memory function. So how we're sampling back through the history of the process is sort of counteracted by the structure that you have because you're fixing that value of A. So I know that this model and the way that we sample from it can be a little bit confusing, especially because we have lots of different cases for A. So I want to talk a little bit about the case where we have a fixed underlying transition matrix. So thinking back to that web browsing example where we're opening up tabs, what we might have is some kind of memory function which incorporates that temporal information alongside some underlying transition matrix. And then rather than thinking about a probability of transition to a particular state, you can reframe this model to think about where could we transition to next. So let's say we're currently a walker at node E in our system, and we're asking questions around what possible transition states can we see under this separable Markov model. And you can really think about it as a probability density over a transition as if you were at the current state, the state before that, and the 2 states before that for a process with memory length 3. And so I've just represented that on the right hand of this slide with sort of these 3 networks. So the top one is a transition from state E, so our current state. And you can see from the underlying transition matrix that from state E, we could transition to state C or state F. And then if we transition from 1 step ago, so we could have been at state A or state D, we could transition to state B or state E, or from 2 steps ago, where we could only be at state B, where we could transition to state A or state C. And so that memory function, sorry, it's kind of a little bit tucked away under here for some of you, basically samples across each of those matrices and draws a transitioning state from this set of possible outcomes. And so what this does is it actually will introduce transitions into our system which don't exist in that underlying transition matrix. So for example, it would be possible to transition from state E to state B in this system if we were currently at state B, but we took a transition from state A. So that would be the case where you sample the lag which you're transitioning from to be 1 step ago. And so when we sample transitions from this system and we represent them with just a network which has a edge weight, which shows how many transitions we store between each 2 nodes, we get a model that looks something like this. And so this is a really sort of nice result, because I think initially you're like, why would you ever use this model? You're introducing transitions which you don't have baked in. But the nice thing is when we have systems with lots of randomness, it allows us to really separate out that temporal information from the structural information. So when you have sort of these messy systems, once you fit the separable Markov model, you can end up with this nice distinction in your parameters between a meaningful underlying transition matrix, which in some cases can have physical meaning and representation, and this temporal memory function, which is related to the autocorrelations on those sequences which you're seeing. And so hopefully everyone is pretty clear about how this separable Markov model works. And the real advantage of this model sits in the space where we can separate that independent history of the process. So it's okay for us to make this separable assumption. And we have data that has long memory length, because that's the space where fitting the full kth order Markov model doesn't really work, because you just need too many parameters. It's really, really hard to fit the model to the data. And so we can come up with a chart which looks something like this. So when we have data and we're looking to fit a model, if we have a separable assumption which works okay, we always prefer the separable model. It's just a subset of the full order Markov model, and it's always preferred when the information you lose by making that separable assumption is less than the information you lose because you can't fit your parameters correctly, because you don't have enough data. The really interesting case is sort of up here, where we have data or settings, so we have a long memory length, so we know that there's a lot of memory in the system, but we also know that we don't want to have a separable assumption. So we want to include that full joint history of the process. And so this is where a lot of my work is at the moment, is determining, given some data, how can we measure aspects of that data to really understand when we will prefer the separable model, because the fitting cost is outweighed by the loss of information you make under this assumption. Or does the data sort of sit in this case, so we do actually need that full k-order joint history of the process, and it doesn't really matter that we can't fit our parameters too well, because we can fit things, we've got really good models for it, and we have the computational power. And so this is like a lot of what I'm thinking about. What I'm thinking about this as a viable model, particularly in complex settings like social systems or economic systems or financial systems. And so a lot of the ways which we're evaluating this separable model kind of fall into 2 bins. The first one is, how can we evaluate the sequences which we're generating from these models? And so that's sort of thinking about, if we're generating these sequences for testing of different metrics or to simulate data or for agent-based model, how can we make sure we're doing what we think we're doing? And then the second sort of bin of evaluation techniques are, how much information do we lose when we fit this separable model over the full kth order Markov model? And so to talk a little bit about how we evaluate dynamics, I know some of you do a little bit of information theory. I promise we're not going to go too much into it. But basically, when you want to think about how much information we contain in a sequence, a really elegant way of doing this is by estimating the size of the typical set. So the typical set is just the set of sequences which have an entropy of that subsequence, which is the same as the source of the process. It's sort of slightly different to the most likely set of sequences, but you can think of it as, if we see one of these sequences that's in the typical set, we have an entropy that's similar to the process. So it's like a typical sequence from this system. And so we have a really nice result in information theory, which links the size of that typical set with the entropy of the process. And lots of maths behind this hand wave, we can think about the size of that typical set as a function of how big the gaps are between matches of subsequences. So if we see a sequence of data represented in blue, and we find a match in that sequence of data that starts at time I, and we match that to something in the history of the process, the size of the gap between those matches and also the length of those matches relates to the entropy of the sequence and the process which we're observing. And so this is the result which we're pulling in here. You'll notice that we have limits. We do have bias in this as we work in the finite space. This bias is pretty constant for sequences of a particular length. So as long as we're thinking about these sort of information theoretic measures in a relative sense, everything holds up okay. And what we can do is we can generate data from both the separable model shown in red and a second order Markov model shown in blue. And what we can see is that we get really similar distributions for both the gap between these matching subsequences and the length of these matching subsequences. And so what that's telling us is that the entropy of the sequences we're generating from these two systems is similar. And so that's at least somewhat reassuring that, at least for simulated data, our separable model can behave in a similar enough way to this second order model. Something else we like to look at is the size of a repeating subsequence. So this is related to a lot of techniques in natural language processing. But what this tells us is about how much memory we have in a system. So whether we can say, I always want to generate repeats of length 5 and nothing greater, can our model capture that? And that gives you a nice bound on how much memory is within your system. Because, for example, with either a full Markov process or a separable process of memory length k, you'll never be able to generate sequences where you only get a subsequence of length k plus 1 and then nothing beyond that. I'm happy to explain why if you ask. But the sort of takeaway from this plot is that when we look at these repeating subsequences for both the second order and the separable model, as well as these information theoretic measures, we get really similar behavior between the separable and the second order model. So even though we're making that quite large assumption that we can linearize that dependency on the historical states of the system, we can still see some really similar behavior between the two models. And so this is reassuring. Now, the way that we're framing this model is as an alternative model to the full kth order Markov process. And so another question we're interested in asking is, when we make these assumptions, so when we choose that linearized dependence, how much information are we losing? And so one really nice way to measure that is to use the Kullback-Leibler divergence. And so what that tells us is how many extra bits of information do we need to encode a sequence using the full Markov model of history length m, given we've already encoded it with our separable process. And so what we can do is we can just substitute in, this is just the Kullback-Leibler divergence formula, and we've just put in the parameterization for that separable Markov model. And so this is a really nice, elegant result, which allows us to, when we fit the separable Markov process to data, determine how much information we're losing by making that separable assumption. So I will sort of preface this part of the presentation by saying these are very, very new results. If there is something that looks wrong, please let me know. But the general procedure which we have for fitting this separable Markov model is, firstly, we evaluate how much memory we have in our system. There are lots of different ways you can do this. There's a nice conditional mutual information test, which people use for fitting kth order Markov models. Here, I'm currently taking quite a straightforward approach, which is I'm fitting our separable model with a long history length. And what we can do is once we fit it, we can look at what that memory function looks like and see, as soon as our system stops giving weight to states in our process, that's probably an appropriate memory length for the system. I sort of highlight that to say this is not how you should do it, but this is how I have done it for the purposes of the data and results which are in this presentation. But if you have ideas about nice ways to evaluate how much memory we're seeing in a data set or in a sequence or in a system, please let me know. I'd be very happy to chat about it. Then what we do is once we've evaluated what an optimal length for that memory process is, is we fit the separable model with all three possible choices for that transition matrix. So we use a fixed underlying transition matrix. So remembering we have no temporal memory in the transition matrix itself. We take the transition matrix to the power of the lag. So in this case, we're looking at the memory created by how many steps we're looking to jump under each of those transitions. And we allow the transition matrix to be completely free. So this is the case where the dynamics of our system can change in sort of the short, medium, and long term. And we fit all of those three models using a 5-fold cross-validation technique. We do some blocking. For those of you who've worked with sequential data, you know how important it is not to lose that ordinal information when you're sampling from your process. And then what we do is, because each of these three models have different parametric requirements, so the fixed and the a to the power of w both are n squared plus k parameters, whereas the free a to the w obviously has a lot more parameters. We want to use a Bayesian information criterion alongside the log likelihood to evaluate which model we want to choose. So once we've selected which variation of our separable model we want to fit, we fit it on the full data or the full training data of this process. And then we're evaluating the performance of the model and comparing how much information we're losing using that callback-Lieber divergence from the full kth order Markov process. So the datasets which I have currently applied this model to, and these are all sort of sub-datasets of these datasets, and all of these datasets are available publicly. So if they will be of interest to you or your research, I can give you the URL, or you should just be able to find them with a quick Google search. But we're really motivated by this process and this problem of predicting sequences. So we think a lot about user activity. So the Last.fm dataset, I'm not sure how many of you will be familiar with Last.fm, slightly before some of our times, I think. It's a music streaming service which links to your Spotify and basically sits on top of it, and you sort of can go through and stream different artists. From this data set, we're not looking at what songs people are listening to, but we construct user trails by looking at what artists they listen to. So it might be like Taylor Swift, Taylor Swift, Taylor Swift, Taylor Swift, Taylor Swift forever. A lot of them are more interesting than that. But this full data set has 19 million entries. So we've got song, user, timestamp. So if that's useful to you, it's a really nice data set. And I've just taken a sample of 50 user trails from that. So we have 337 points across 50 sequences. The second data set is a user check-in data set. So it's the Bright Kite data set. The data set contains data for over 700,000 locations and around 52,000 users, but we've just taken a sample of 2,100 check-ins. I think they're from 30 users. The Wikipedia dataset, this is a user trail dataset, so we're seeing what links people are navigating between. So this one's a really key one for sort of that motivation behind this problem. But Wikipedia is just a game that people play on Wikipedia, so they use a slightly smaller version of Wikipedia, and the goal is to get from one page to another page in as few clicks as possible. So you might start on the United States and the goal is to get to tennis, and you can do that in very few clicks, as you'll see a little bit later. In this set, we've sampled a selection of the parts where that final page is an Olympic sport. So I'll show you some results from this data set at the end of the presentation. The next one is the Rota's distribution data set. So we have news articles, so we're looking at natural language. And we also have some mobility location data, which is just some mobile phones. So all of these are relatively small data sets. And what we can do is, once we fit that separable model, so we fit the separable model with a fixed a to the power of w, and a free underlying transition matrix. And what this table is showing you is each row represents a single data set. This column here represents the lag at the percentile at which we've counted for 95% of the temporal memory in that memory function. So we fit for these data sets the model with a long memory, and we just looked at how quickly that lag, that memory function, dropped off. And so we can see that for some of these data sets, we have quite a long memory in the system. And for some of these data sets, we have quite a short memory in the system. And then what we do is we fit the separable model under each of those three cases. the numbers here, the top number is the log likelihood and the bottom number is the Bayesian information criterion. We are selecting the best model using that Bayesian information criterion because we have this discrepancy with the number of parameters between the separable model where we have a fixed transition matrix and the separable model where we have a completely free transition matrix. You'll see the log likelihoods for the free matrix are almost always as good as or better than for the fixed transition matrix, which is expected. And then what we do is we fit the model to the full training set of this data, and we can calculate the KL divergence between this fit separable model and the full Markov process. And so what you can see here, I actually forgot to put this bit on the slide, which is probably one of the more important bits, but in the Last.fm, Brightkite, Wikipedia, and Reuters dataset, I haven't yet run it for the mobile trajectory dataset, we get equivalent or better performance under this separable Markov process than when we fit the full kth order Markov model. And the reason is particularly in these settings where you have a longer temporal memory, you just need too many parameters to fit that full Markov model, and you end up with overfitting in your system. So we have these models which outperform the full kth order process. We can fit them quite robustly. And in general, we're not losing that much information when we're making that separable assumption. So to sort of come back to that conceptual chart I had before, we can look at how good our separable assumption is, so how much information we're losing when we make that assumption. So that's sort of the KL divergence along the x-axis of this chart. And then we can also evaluate the temporal memory. So that's just using the process which I mentioned earlier. And I just have for all 5 of those data sets where they sit on this chart. So like I sort of hinted at toward the start of this talk, I'm really interested in potentially data sets which sit up in the top region of this chart. So we have longer temporal memory. And so I've sort of got a set of data sets to test this on. But if you do have any ideas that you think might work well, please let me know. And to show you an example of what this looks like, so this is from the Wikipedia dataset. So the game where you start on one Wikipedia page to get to another Wikipedia page. This in particular is the subset of that game where the goal is to get to the Wikipedia page for tennis, inspired by recent activity on level 10. And what you can see is in these user paths, we do have a little bit of memory in the system. So up in the top left, you can see that memory function. So often we're transitioning as if we were at the current state or 2 steps ago. But what's really nice is we get this very interpretable underlying transition matrix. And there's a little bit which sort of falls off the bottom of the slide here, which I've included. But you have sort of these paths that all lead in toward this tennis game. I mentioned these are very preliminary results. These are from like the last 2 weeks. And sort of the goal more generally is to work out whether we can fit this model and get really interpretable memory functions and really interpretable transition matrices for sort of more complicated settings. And so that's kind of an overview of the process and the model and how we fit it so far. And to wrap up my talk, here are some of the references which I've mentioned. I want to summarize by saying the separable model has a really nice low parametric requirement. It can capture dynamics with long range memory, and it offers a really nice alternative to the full kth order Markov process. I'm around until Friday, so please let me know if you would like to chat or grab coffee, talk about your research or my research. This is also one of my projects. So I've previously done quite a bit of work looking at information flow estimation online, which I've linked up here. And then this is some of the more preliminary work I did in this space. And thank you for listening.
Thank you. What's time for questions?
So thank you for your talk. So we talked about the weight function. You said you get it from a probability density over all possible previous states. So you just do sampling of what all the possible previous states are, and then that's how you construct. Yeah, correct.
So when we fit the model, we use an expectation maximization procedure. So you do like a two-step optimization, and luckily, luckily this separates really nicely onto the log likelihood. So what you can do is you can optimize for the weights in that memory function, which generally we initialize with just a uniform distribution. And so then what we do is the way that you can think about it is we assign each of those transitions to a particular jump or to a particular lag, and then we optimize that transition matrix, and then you sort of repeat that process iteratively until you've like reached an optima for each of the memory function and that transition matrix. So it's nice in that there's like a nice optimization procedure we can use there. But I think your question sort of sits more generally along like, how do we think about what this memory function represents in the system, and how does it relate to the sequences which we're seeing? Is that correct?
I think what you said earlier, my follow-up question was, is that optimization the same that you do for when you let the transition matrix be free, you basically fit all powers or all 9 powers?
Yeah, it's pretty similar. The like log likelihood function is obviously exactly the same. The difference is that constraint that you have on that matrix. So it becomes actually, in the case where the transition matrix is fully fixed or fully free, we can just use Lagrange constraints and it comes out very nicely. In the case where we have our transition matrix A to the W, you actually need to do numerical optimization for that because there isn't a nice analytic solution. But yeah, once it's free, and this is sort of an interesting distinction, which is that the system becomes ill-constrained. So you can have the same model which generates the same sequences because you sort of move that temporal memory between that memory function and the underlying transition matrix.
Any questions? Can you go to the tennis example for a second? You're saying that like one of the goals is to find some of these memory functions that's interpretable. Can you like cartoon what that interpretability would be? What would it mean?
Yeah. I'll sort of answer this badly first, and then I'll come back and actually answer your question, which is, so this is from like this paper here. And basically what we did was we started with a very simple Markov process, and we are generating sequences from that process, and we're actually controlling what that memory function looks like. So in these charts, the top, like the red charts here are representing that memory function, so where the weight sits. And then the bottom of these is the correlation within the generated sequences. So we calculated that using our Cramer's V statistic, which is basically an autocorrelation function, if you squint hard enough. And what this shows is if we sort of change the shape of that memory function, the correlations in the sequences sort of change to match that. And so the goal is when we fit it to data, we can get something which tells us a little bit about how the system is behaving in like where it's transitioning from. So you can think about some really interesting examples where the memory function is really negatively skewed. And so what that can tell us is the goal would be is to, if we can find sort of more simple representations of these underlying matrices for complex systems, so we have lots of interesting transitions, and then potentially a lot of that complexity can just be captured in the sort of temporal memory aspect of that system or in that memory function.
The somewhat related one, that was helpful. So if I take the Wikipedia data, for example, and just like have some knob that randomly shuffles the order of pairs of entries, is there some way that I could see on the information loss versus memory chart, like where that's that'll probably increase the divergence?
So you have your Wikipedia data,
Yeah, starting at like North America, going to United States, for instance.
Yeah.
And I have a lot of instances of these sequences. And if I fully shuffle the order of all of them, then there's not much structural information. And I would imagine the memory would also either blow up or disappear?
Yeah, so when things become more random, your memory tends to disappear. And that's actually how I did some of the validation for the KL divergence as a measure that it was behaving in the way you expect. Because if you have a system where you're just randomly shuffling things, you generally don't need memory in that system to capture it, so the divergence becomes zero.
Trying to find some like way to get you up to the top left part of the divergence memory.
Yeah.
Yeah, I guess, yeah, how would you, what types of data sets or what types of processes?
Yeah, so the thinking is that sort of more like human-centric social data sets, people will behave with memory. But the problem is often these data sets are really noisy and we have low quality data and they're really hard to fit. And so it's kind of that perfect use case for getting up to the top left of that chart. So systems with like long memory and bad data is kind of not the dream, but my particular dream for this project. And so at the moment, I'm in the process of exploring different data options. And I've got access to some interesting economic data through my affiliation with the Institute for New Economic Thinking in Oxford. So that's sort of the next few weeks' plan.
Other questions? How would you interpret this? How would you interpret it to understand sort of the language?
Yeah, so I would really love to have like a nice result here, which says that the underlying transition matrix will always tell you really useful, interesting things about the system. It's a new project. That is something I'm currently working on. The thinking is that when you fit this to systems, that hopefully the underlying transition matrix is meaningful. I feel like saying meaningful, like in this kind of work, is always like a little bit nuanced in that it depends a lot on the system you're thinking about and how you're thinking about it. And like physical systems, like web pages, links, all of these links exist in between these Wikipedia pages. And so that's like one way you can verify it. But this question of like, when we have an underlying transition matrix, is it meaningful, is a lot harder to answer when we have a social system and we're thinking about like, maybe we're looking at, and this is one of the data sets which I sort of think might fall into that top left corner, but I have sort of conversation transitions from some social media data sets which I collected for some of my other work. And so it's like, how do you verify that there is actually a meaningful underlying link between like two different topics of conversation? That's a really, really hard problem. And so I think that ideally we can come up with like a nice result which links this memory function with a correlation structure from those generated sequences. So you can show that it's capturing some kind of temporal information. But in general, I would say it's very hard to actually determine whether the parameters you're coming at are meaningful or interpretable. But that's definitely what we're striving toward.
Other questions?
Yeah, I can try one. Yeah, I'm familiar with Markov chains, and so if you have a stochastic processes, then you can estimate the matrix, and you can find negative values and the vector and find the steady state. Have you seen something similar like that? Because so you have like memory, like 3-4 time steps. Have you seen any methods of like doing a similar process to find steady states?
Yeah, so
Predict where it's gonna eventually fall.
once you fit this model, you can calculate what the steady state distribution looks like in a really similar way you do with like a regular Markov chain. The problem is, and what you run into a little bit with fitting, is that the mixing time on these systems when you have longer memory is obviously much slower because you tend to sit around like particular parts of your system. And so what you can do is, if you, particularly in the case, I should not have put this so far back, particularly in case 2, where we're incorporating that temporal information into the lags, you can reframe this as basically a resampling of the Markov process. And so you can start to pull in some really nice Bayesian results that allow you to sort of correct for that bias. Yeah, for method 3, you can calculate that steady state distribution, and like the mixing time will be much slower than for like a full Markov process. I'm not exactly sure how it compares to the equivalent like kth order Markov process. My intuition is that it would depend on how well